Hello everyone, thank you for checking out this video. You are with Coach Jordan from Territory Academy. Now let us begin looking at question 2. We need to find the total number of positive integers n, whereby n has a lower limit of 10 inclusive and upper limit of 100 inclusive, such that n squared minus 9 divided by n squared minus 7 gives us a fraction in its lowest terms. So let us first observe this fraction really quickly. So what we are presented with is n squared minus 9 over n squared minus 7. And you realize that the numerator and the denominator are really close in terms of value. In fact, if we extract one whole, this is equivalent to 1 minus 2 over n squared minus 7. And you realize that for this original fraction to already exist in its lowest terms, we require this to be in its lowest terms as well. And for 2 over n squared minus 7 to be its most simplified form, we simply require for 2 and n squared minus 7 not to share any common factors. Therefore, to put it simply, we need the greatest common divisor between 2 as well as n squared minus 7 to be equals to 1, to indicate that they do not share any common factors. Hence, what we really need to do is to ensure that n squared minus 7 in the denominator is not an even number. As long as n squared minus 7 is an odd number, we guarantee that this is still going to be a fraction in its lowest term. And you realize that for n squared minus 7 to be an odd number, right, we need n squared itself to be an even number. And for n squared to be an even number, you guessed it, we require n itself to be even as well. Therefore, this entire question really boils down to how many even numbers there are in between the upper limits of 100 and the lower limit of 10, and that would then give us the answer. So, keeping in mind that these are our limits, how many possible values, even values of n do we really have? We would have to look at 100 minus 10 over 2, because we are only sieving out the even values, which alternate with the odd values, and we have to add 1. And this will then give us an answer of 46. And therefore this will give us our final answer. Now let us begin looking at question 3. Here, we are required to evaluate this never-ending surd expression in its simplest form. The challenge here is obviously that the sequence itself is never terminating, and on top of that, we notice that the same numbers are recurring over and over again. Now, how do we make use of this in order to solve the question? Now, one common technique that we usually take advantage of with regards to these kinds of questions would be to let x take the value of this entire expression that we are trying to look for. So x is going to be equal to square root of 2008 plus 2007 times the square root of 2008 plus 2007, so on and so forth. Alright, so I'll just be writing out 2 iterations, but it is understood that it doesn't terminate. In which case, we could actually express the rest of the sequence in the form of x itself. Because in this case, x is equals to the square root of 2008 plus 2007, and you realize that from this sequence onwards, from this term onwards, everything else is essentially x all over again. Therefore, this entire chunk can essentially be substituted with x itself. And from this stage, we could square both sides. And what essentially results from this is simply a quadratic equation that can be solved rather simply. So by shifting all the terms to the left-hand side, this is what we have, and this can then be factorized rather nicely. Into x plus 1 times x minus 2008. And at this stage, there are 2 solutions, and it is rather obvious which one we have to reject. Between -1 and 2008, first of all, -1, the numerical value itself doesn't make much sense, given that we're dealing with these numbers. And secondly, it can't be negative because the question here has clearly defined this entire value to be a positive square root. Therefore, we would have to reject -1. But when it comes to 2008, this is the more plausible solution. And therefore, x equals to 2008 is going to be our final answer. Now let us begin looking at the fourth question, which requires us to find the maximum value of the sum of these two sets. One being the square root of x minus 144, the other being square root of 722 minus x. So how do we begin approaching such questions? Now the first thing to take note of is that the nature of x in the first set is actually a positive x, whereas it is actually negative in the second set expression. So these are the clues that allow us to take advantage of the fact that the inequality involving arithmetic mean as well as geometric mean can be used in this case, or we refer to it as AMGM inequality for short. Right? So for those of you who might not be familiar with this inequality, that's all right. We'll take just maybe a minute or two to show how this is being derived. So we can start from a simple expression such as the square of the difference of a minus b, and we know for a fact that squares at the bare minimum have to be greater than or equal to 0. Now, by expanding this is what we have on the left, this is what we have on the right. And we can actually complete the square in order to morph this into an expression that involves a plus b squared instead. And this is how that's being done. And you realize that we add 2ab here and we subtract 4ab so that we keep the total value consistent throughout. Now this portion can then be factorized into a plus b squared minus 4ab greater than or equals to 0. We can then shift 4ab to the right hand side of the inequality. And this is what we have. Onwards, we can proceed to square root both sides of the inequality. And we get a plus b greater than or equals to 2 times of root ab. After which we can then divide both sides of the inequality by 2. And we essentially reach the overarching inequality between AM and GM, right? The arithmetic mean on our left, the geometric mean on our right. So given that A and B are real numbers, we know for sure that the maximum value of root AB is kept at the average value of A and B. And it turns out that this result is rather crucial in solving this question today, because we can actually do some manipulation to this result in order to link it back to the statement given by the question. Now the question is, how so? Now actually we can pick up where we left off from this step over here, because if we were to add a and b to both sides of this inequality, what we realize is that we have 2 times a plus b greater than or equals to a plus 2 root ab plus b. And the reason why I'm writing a and b in this specific format is to illustrate that actually a plus 2 root ab plus b is actually a square of root a plus root b. In which case, we will be able to then square root both sides of this inequality, and we can therefore claim that the root of 2 times of a plus b has to be greater than or equal to the sum of root a plus root b. Now, how do we relate this back to the question? So this result over here, right? Remember that we are trying to find the maximum value of the sum of two set expressions, which therefore correlates to whatever we have on the right hand side of this inequality. So if x minus 144 is our a, and if 722 minus x happens to be our b, then what we want to find is really what is the square root of 2 times of a plus b. Hence, we can let a be equals to x minus 144. Similarly, we'll let b be equals to 722 minus x. And therefore, we would be able to see that the maximum value is denoted by this expression on the left-hand side of the inequality. So therefore the maximum value will be equals to the square root of 2 times of a plus b. And if you look really carefully, because we stated initially that x was positive here, yet it's negative over here, the sum of a and b will result in the x's being struck off. And what we really have left behind is the sum of 722 and negative 144. And this is going to give us 578. And if we multiply that by 2, we will arrive at 1156, which happens to be a really nice square number for us. Right? If you happen to square root this, you will realize that we get 34 as the final answer. And since this occurs on the left-hand side of this inequality, that would then suggest that is the maximum value of root a plus root b, which is also the maximum value of the sum of this expression that we are given. Hence, 34 is our final answer. Now, let us begin looking at question 5. We are asked to find the least integer that is greater than the square of the sum of 2 plus root 3. Now, since we obviously don't have any access to calculators, finding the exact value of this square is going to be a tad difficult. However, what we can do is to compare these values to other relevant surrounding values that we can be sure of. So first, let us expand this square to see what we have. We could make use of your identity, a plus b squared, to give us a squared plus 2ab plus b squared, and that will give us 4 plus 4 root 3 plus 3. And simplify, we have 7 plus 4 root 3. Now, clearly 7 isn't the issue. The issue lies in 4 root 3, so we have to devise a way to get rid of it somehow. And one neat technique that we could employ would be to introduce the conjugate set 2 minus root 3, and we square this instead. And let us see whether we get a similar expression. So this time we are making use of the identity a minus b squared to arrive at 2 squared minus 2ab plus b squared. And you realize that since our a squared plus b squared terms stay exactly the same, the only change really occurs here, whereby this is a minus instead of a plus from earlier. And therefore, we can circumvent the above steps and jump straight to the conclusion that 7 minus 4 root 3 is the value for this. Now, this is useful for us because, as observed, we can see that on one hand we have 4 root 3 being positive here, and we have 4 root 3 being negative here. Therefore, by taking the sum of these two expressions, we can effectively remove 4 root 3. And therefore, this would just be the sum of the two copies of 7, which gives us 14. However, that's not quite going to be our answer quite yet, or rather we still have certain justifications to be done with regards to the value of 2 minus root 3 squared. Now, even though we do not have a grasp of its exact value, of its exact numerical value, we do know that root 3 lies somewhere in between 1.6 and 1.8, right? It is going to be 1.7 something, because 1.7 squared is 2.89, and furthermore, I know that 1.8 squared is going to be 3.24. So root 3 has to lie somewhere in between 1.7 and 1.8. So given that we understand that, we then also know that 2 minus root 3 has to be greater than what? Of course, it is greater than 0 as well, because 2 is just equivalent to root 4. And this is crucial for us because if we do know that this difference lies in between 1 and 0, squaring this same difference is not going to change its value by that much, right? Any value in between 0 and 1, when squared, is still going to lie in between the regions of 0 and 1, right? And this is crucial for us because I now know that if this value here that we are adding to the expression that we are trying to find a value for is less than 1 and is more than 0, then we know for a fact that this expression, the square of the sum of 2 plus root 3, has to be greater than 13, right? And because we know for a fact that this is greater than 13, since we are asked to find the least integer that is greater than this expression, then the least integer that we are looking for would have to be 14. And hence this is our final answer. We have completed this lesson. Thank you for watching this video, and I hope you have enjoyed today's lesson. Goodbye and see you again in another lesson.
If you would like to learn more from these tutorials, please smash that like and subscribe button.